Okay, I'm going to talk about another nice feature of Euler's totient function. Well, I'll just write it out and then I'll prove it. Sigma d divides n mu of d over d. So this is Euler's totient function again. Totient function. Number of numbers not exceeding n, relatively prime to it, equals n times the sum over divisors of n of mu of d over d. And this thing here is the Möbius function. The one that comes out to be 0 if it's got a square in it. Well, let's just prove that. Well, I'm going to remind you that phi of n is multiplicative, and that tells us that f of n equals the sum over d divides n of phi of n is also multiplicative. And we established in the last screencast that this equals n. So f of n was just n for any value, and that was sigma over d divides n of phi of n. And now what I'm going to do is I'm going to use the Möbius inversion formula. Möbius inversion formula. Let me write that out again, and we'll play with this and see what happens. So if f of n equals if sigma over d divides n of f of d, then f of d equals f of n, the sum over d divides n of mu of d little f of, that's big F of n over d. Or we could even write it down the other way, d divides n, mu of n over d times big F of d. Okay, so what's that equal to? Well, that's equal to, let's choose this one here, sigma over d divides n of mu of d times capital F of n over d. Well, we know what that is. We know what big F is. Big F of any number is just the same thing, because we established that on the last screencast. So this thing is equal to sigma over d divides n, mu of d times n over d. And then we'll observe that n doesn't change, so it's n times sigma d divides n mu of d over d. Done. What was this whole thing equal to? This thing was equal to little f of n, which in this case was phi of n. So we've got this rather nice little formula here. Phi of n equals n times sum over d divides n mu of d over d, which is quite nice. Let's just try this. Try with n equals 20. So phi of 20, and we know what that is. Let's just check. N times, well, it's going to be mu of 1 over 1 plus mu of 2 over 2 plus mu of 4 over 4. Don't need that, because mu of 4 is equal to 0. 5 goes into it, doesn't it? Mu of 10 over 10 plus mu of 20 over 20. Don't need that. Of course, we don't need this one, but we don't need this term here or this one here because they've got squares in them. So what have we got? We've got n times mu of 1 plus a half mu of 2 plus a fifth mu of 5 plus a tenth mu of 10. Let's have a look at that. N times 1 plus, what's mu of 2? Well, it's just minus 1, isn't it, over 2. What's mu of 5? That's just going to be minus 1 as well, plus, that's going to be a plus 1 over 10. Equals n times 11 11 tenths, we've got 10 tenths there and 1 there, minus 5 tenths from here, minus 2 tenths. What's gone wrong here? We've got 11 there, minus a half, minus a fifth. So altogether we've got 7 tenths. Oh, that's right, that's right, that's right. Equals 20 times 11 minus 5 is 6, minus 2 again is 4 over 10, equals 1 of those tens equals 8. So I'm asserting that phi of 20 equals 8. Well, let's just check from our formula. It should be 20 times 1 minus 1 half times 1 minus 1 fifth equals 10 times 4 fifths equals 8. Check. It's as well to verify this kind of thing. I think this shows how subtle this inversion formula actually is. We've got rather a lot going on here. There's quite a lot of non-obvious cancellations going out. And of course it will be a lot more difficult if you had a rather larger number, 14,728. It will be a different matter to do that, and it will be a lot easier to use this formula rather than to go through the mechanics. Okay, I'm going to stop there.